Section 12.4, Tangent and Normal Vectors. Before I get into this section, I wanted to point out something that was brought to my attention regarding WebAssign. When you are trying to input a vector in WebAssign, like adding the +C vector, in print, we denote vectors by boldface type. When we're handwriting, we denote them with the arrow above the letter in question. On WebAssign, they want the boldface. So on the input tools under vectors, the very first box there is the boldface type box. You click that and then you can type a vector in boldface and it'll accept that for you. Okay? All right, so back to the tangent vector. The tangent vector is the vector that is tangent. Deep thought there. That is tangent to a curve at some point t. And has magnitude 1. Okay, so the tangent vector is a unit vector. Okay, it's denoted capital T of t. So capital T for the tangent vector. Okay, so given a curve r of t, r prime of t, aka v of t, is tangent to r of t. Okay, so then if we normalize that derivative, r prime of t, if we normalize that, we have our tangent vector. So t of t is equal to r prime of t divided by the magnitude of r prime of t. So we're just normalizing that vector. All right, so let's do an example. Leave that where we can see it. Find the tangent vector t of t at t equal to 1 for r of t equal to t in the I direction plus t squared j. Okay, so first things first, we find r prime of t. So that's going to be I plus 2tj. There we go. Now we normalize it. So the magnitude of r prime of t, that's going to be equal to 1 plus 4t squared square root. So then the tangent vector is just going to be equal to I plus 2tj divided by the square root of 1 plus 4t squared. And of course we can put that in vector notation as 1 to t over the square root of 1 plus 4t squared. And we could go a step further if we really wanted to and say this is the vector 1 divided by the square root of 1 plus 4t squared, comma 2t divided by the square root of 1 plus 4t squared, if we wanted to really take it down to its simplest form. Okay, and we were asked to find this at t equal to 1. So t of 1 is going to be equal to the vector 1 over the square root of 1 plus 4 times 1 squared, comma 2 times 1 over the square root of 1 plus 4 times 1 squared. So that's equal to 1 over the square root of 5, comma 2 over the square root of 5. And there we have it, our tangent vector. Okay, so now let's do a different example here. So example, we are going to find the tangent vector t of t for r of t equal to 2 cosine of t in the I direction plus 2 sine t in the j direction plus t in the k direction. Okay. And then find a parametric representation so a parametric representation of the tangent line at the point root 2 pi over 4. Okay. All right, so this shouldn't be too bad. The tangent vector is going in the same direction as the tangent line. So the tangent vector is going to be our direction vector for the tangent line. So once we have that tangent vector at this point, it shouldn't be such a big thing. So let's go ahead and get started here. So our tangent vector is going to be r prime of t divided by its magnitude. Okay. So we need to know what is r prime of t. So let's take the derivative of r. So this is going to become negative 2 sine of t in the I direction, plus 2 cosine of t in the j direction, plus 1 in the k direction. Okay, so then the magnitude of that is going to be the square root of negative 2 sine of t quantity squared, plus 2 cosine of t quantity squared, plus 1 squared. So that's going to be the square root of 4 sine squared t plus 4 cosine squared t plus 1. So that's going to be, let's see here, 4 times sine squared t plus cosine squared t plus 1. Cosine squared plus sine squared is 1, so this is just equal to root 5. All right then, so our tangent vector is the vector negative 2 sine t I'm doing this in component form, comma, 2 cosine t, comma, 1, divided by root 5, which we can simplify a bit to get negative 2 over root 5 sine of t, 2 over root 5 cosine of t, 1 over root 5. Okay, and we were asked to, well, let me put a box around this. This is our tangent vector. Okay, and then we were asked to find the parametric representation of the tangent line at a specific point. So what we have to do is find the t that gives us the position root 2 pi over 4, and then use that t to find out what the actual tangent vector is at that point. Okay, so this is the tangent vector for any t. Now we have to find the t such that r of t is equal to, and I can leave that as a vector, root 2 pi over 4. Okay, well, let's go back to r of t then. So r of t was equal to 2 cosine t, 2 sine t, t. Okay, well, that makes this pretty simple. That means that t is equal to pi over 4. So what I'm doing here is I'm looking at the z components. So the z component is pi over 4. T is the z component. T is equal to pi over 4. So that was pretty straightforward. We can check it by plugging pi over 4 into each of the other components. 2 times cosine of pi over 4 is 2 times root 2 over 2, which is root 2. 2 times sine of pi over 4 is 2 times root 2 over 2, which is root 2. So the t in question is definitely pi over 4. All right then, so the direction vector for our tangent line is going to be t of pi over 4. So that's going to be negative 2 over root 5 times sine of pi over 4, comma, 2 over root 5 cosine of pi over 4, comma, 1 over root 5. Okay, let me switch back to white. All right, so this is going to be negative 2 over root 5 times root 2 over 2, comma, 2 over root 5 times root 2 over 2, comma, 1 over root 5. So that vector comes out to be negative square root of 2/5, positive square root of 2/5, and then 1 over root 5. Okay, great. So now we need to use this direction vector and our point to find the parametric representation of our lines. So remember, the direction vectors are going to be the multiples of t that we add on to the original values for the point that we're looking for. Okay, so x is going to be equal to, the point was root 2 pi over 4, so we begin at root 2, and then we add negative square root of 2/5 multiples of t. Y began at root 2 as well, and here we are going to add positive square root of 2/5 multiples of t, and then z is equal to pi over 4 plus 1 over square root of 5 multiples of t. All right, so I can simplify x a little bit here. and then y and z are as they are. Okay, and there it is, our parametric representation of the tangent line at the point root 2 pi over 4. All right, so now let's talk about the normal vector, or more specifically, the principal unit normal vector. Okay, this is n of t for normal, and that's equal to t prime divided by the magnitude of t prime. And these are of t. Probably should put that in there. Okay. So now we're going to find the derivative of t, the tangent vector, and we're going to normalize that. And that gives us our principal unit normal vector. And again, this is a unit vector, has magnitude 1. All right, so a couple of things here really quickly. First of all, if I dot t with itself, this is just equal to the magnitude of t squared, because that's what it is when you find the magnitude, right? You square it, you just get the vector dotted with itself. Well, in this case, that magnitude is equal to 1 because it's a unit vector. So 1 squared is equal to 1. Now, recall the properties of the dot products. If we were then to dot t with its own derivative, we're going to get 0, right? So that came from our properties. Let me write this down. So recall our properties here. If u dot v is equal to a constant c, then u dotted with the derivative of v is equal to 0. That comes right out of those properties of the dot product for the vectors. Okay, now, if the dot product is 0, remember what that means. That means that the two vectors are perpendicular. The angle between them is 90 degrees. So t is perpendicular to t prime. Okay, so all of this is coming out of the properties of our vectors. Oh, and just to make it really clear, this symbol right here is the symbol for perpendicular. So just in case you haven't seen that before or don't remember that, that's the symbol for perpendicular. All right, so let's put a box around this so that we can keep track of it. Okay. All right, so let's do an example where we're asked to find the principal unit normal vector. So find n of t and n of 1 for r of t equal to 3t in the I direction plus 2t squared in the j direction. Oh, but before we do move on to this example, I wanted to point out one thing really quickly. Please be aware that t prime of t is not the acceleration vector. Okay, t prime of t is the derivative of the normalized vector, the normalized velocity vector. So whenever we take that derivative, we are not getting the acceleration vector. So I just want to make sure you're aware of that before we move on. Okay, so moving on now to our example. If I'm going to find n of t for r of t here, I'm going to have to first find t, the tangent vector. So we've got t of t is equal to r prime of t divided by the magnitude of r prime of t. Okay. All right, so 3t I plus 2t squared j, that is going to have a derivative of 3 4t. Okay. And the magnitude of that is 9 plus 16t squared if we square both components and add them together. All right, so that is our tangent vector. I'm going to rewrite this just a little bit as 9 plus 16t squared to the negative 1/2 times the vector 3 4t, and I'll tell you why I chose to do that. You may recall when we were talking about the properties of the derivatives of vector valued functions, that there was one formula that said, let me get in a color here, if we had d by dt of w of t times r of t, where w was a normal regular function, not a vector, and r was a vector valued function, that this came out to be w prime of t times the vector valued function plus w of t times the derivative of the vector valued function. So really it's just the product rule in play here. Okay, that's exactly what we're going to do here. We have a regular function in t and then a vector valued function. Alrighty, so let's see here. If I'm going to find n of t, we know that that's equal to t prime of t divided by the magnitude of t prime of t. So the first thing I'm going to have to do is find t prime of t. Okay, so we're going to do exactly what we have here in the blue above. We're going to take the derivative of the regular function. So that's going to be negative 1/2 times 9 plus 16t squared to the negative 3/2, okay, times 32t, because we're chaining on the derivative here, times 3 comma 4t, the vector, plus, okay, 9 plus 16t squared to the negative 1/2 times the derivative of 3, 4t, the vector, is 0, 4. Okay, so now I'd like to be able to simplify this as much as possible. So what I'm going to do is a little bit of clever algebraic manipulation. I'm going to go ahead and multiply this by 9 plus 16t squared over 9 plus 16t squared. Okay? All right, so that's just multiplying by 1, so no values are changed. So this becomes negative 1/2. Oh, actually, you know what? Before I write that down, let's note that the 32 and the 2 will cancel out, leaving us with 16. So this will be negative 16t times 9 plus 16t squared to the negative 3/2 times the vector 3, 4t, plus, okay, so if I do this, I've got 9 plus 16t squared to the negative 1/2 times 9 plus 16t squared to the positive 1 times 9 plus 16t squared to the negative 1. If I move this to the numerator, give it a negative exponent, right? Okay, and then that is being multiplied by the vector 0, 4. Okay, so this is negative 16t times 9 plus 16t squared to the negative 3/2 times 3, 4t, plus, okay, so when I combine these two, I add those exponents together and I get 9 plus 16t squared to the negative 3/2 times 9 plus 16t squared times 0, 4. And you might be asking yourself, did I really have to multiply this to factor that out? And the answer is no, because what I'm going for, guys, is I'm trying to factor out this 9 plus 16t squared to the negative 3/2. No, I could have factored out 9 plus 16t squared to the negative 3/2 right off the bat. However, I wanted everyone to see why, when I do that, it left behind a 9 plus 16t squared. Okay, so let's go ahead and factor that thing to the negative 3/2 out. So this is 9 plus 16t squared to the negative 3/2 times negative 16t times the vector 3, 4t plus 9 plus 16t squared times the vector 0, 4. Okay, now the reason I'm doing it this way is because I want us to have something easier to work with, because I'm about to have to take the magnitude of this, and that's going to be super gross if I don't do some simplification. So then that gives us 9 plus 16t squared to the negative 3/2 times, okay, distribute the negative 16t, we get the vector negative 48t comma negative 64t squared, plus, now distribute the 9 plus 16t squared, we get the vector 0, 4, well, I can just distribute that, can't I? 9 times 4 is 36, plus 16 times 4 is 64t squared. Right. Add those two vectors together, we get 9 plus 16t squared to the negative 3/2 times, okay, adding corresponding components, the first component is negative 48t, second component, the negative 64 and 64t squares will cancel, leaving us with just 36. Cool. So that is t prime of t. All right, so now what we have to do is we have to find the magnitude of this thing. Okay, so the magnitude of this is going to be the square root of each component squared added together. So the magnitude is going to be equal to, okay, so this is going to be the square root of 9 plus 16t squared to the negative 3/2 times negative 48t quantity squared plus 9 plus 16t squared to the negative 3/2 times 36 quantity squared. All right, so in one step I've distributed the function in front into the vector and then found the squares of each component and put them in here. So we can simplify that significantly. So that's going to be 9 plus 16t squared to the negative 3 times 48 negative, well, the negative is going to become positive, so whatever 48 is squared times t squared, plus 9 plus 16t squared cubed, I'm sorry, to the negative 3, times 36 squared. Okay. So I'm going to factor out the 9 plus 16t squared to the negative 3, and because we're taking the square root of that, it's going to be to the negative 3/2 times the square root of 48 squared times t squared plus 36 squared. Okay, so now we can find t. I'm sorry, not t, n. Now we can find n. All right, so n of t is equal to, okay, we need to find t prime. So that's 9 plus 16t squared to the negative 3/2 times the vector negative 48t comma 36 divided by the magnitude is 9 plus 16t squared to the negative 3/2 times the square root of 48 squared t squared plus 36 squared. So that's nice. We get some good cancellation. Okay, so this is equal to negative 48t 36. That's our vector. And 48 squared and 36 squared. So clearly we have some 12s going on in here. 48 is 12 times 4. So this is 12 squared times 4t squared. 36, oh, I'm sorry, 4 squared. There we go, 4t squared. 36 is 12 times 3, so that's going to be 12 squared times 3 squared. So that 12 squared will factor out, and then we can take the square root. So we get negative 48t comma 36 divided by 12 times the square root of. So that'll be 16t squared plus 9. And that can be simplified just a little bit more with this 12 here. We can put that in. So this is going to be negative 4t 3 divided by the square root of 16t squared plus 9, and if we want we can incorporate that into the vector, so we can just distribute the scalar, in other words. So that's negative 4t over the square root of 16t squared plus 9 comma 3 over the square root of 16t squared plus 9, and there's our normal unit, our principal unit normal vector. Put a box around that. Done. Okay, so that'll wrap it up for this section. As always, if you have any questions, please let me know. Wait, I hope you're still with me because I totally missed a section. We need to keep going. I need to talk to you a little bit about the tangential and normal components of acceleration. I almost missed that one. Let's get that in here before I shut this one down. So, tangential and normal components of acceleration. Okay, first of all, theorem 12.4 tells us this. It says that if r of t is the position vector, for a smooth curve C, and n of t exists, not n prime, n of t exists, then the acceleration vector, I can spell, hang on one second, acceleration vector A of t lies in the plane determined by the tangent vector and the principal unit normal vector. So the acceleration vector A of t lies in the plane determined by t of t and n of t. So that gives us that a of t is equal to a sub t times t of t plus a sub n times n of t. Okay, so we are determining this plane not in i's and j's, but by t and n, by the tangent and the normal vectors. So we have components for each of those directional vectors, and we add those up, and that gives us our vector a of t. So that's our acceleration. Now we have some nice formulas for finding a sub t and a sub n. Okay, we have, I'll put a box around that. We have a sub t is equal to d by dt of the velocity, or rather the magnitude of the velocity vector. There we go. Okay, so that's equal to a dotted with t, which is equal to v dotted with a, all these are vectors, divided by the magnitude of v. Okay, and then a sub n, that's going to be equal to the magnitude of the velocity times the magnitude of the tangent vector. So that's going to be a dotted with n, which is equal to the magnitude of v cross a divided by the magnitude of v, which is equal to the square root of the magnitude of the acceleration vector squared minus a sub t squared. Okay, so these are the formulas that we can use to find a sub t and a sub n, which are the components of the acceleration vector in the t direction and in the n direction. And one last thing here is that a sub n is the normal component, is also known as the centripetal component, is also known as, aka, the centripetal component of acceleration. Okay, so that is the end of this section. So my apologies for not getting that in there sooner. I hope you stayed with it for the rest of this, just a couple of minutes here. But as always, if you have questions, do let me know.